How are you guys? Welcome back to my YouTube channel. Today we'll be dealing with strength of material N6. We'll be focusing on thick cylinder. Here we have given example 1.3 single cylinder with internal. We have internal and external pressure both there. So nevertheless, we have given a question here says a cylinder with closed ends has internal diameter of 450 millimeter and internal diameter of 150. It is subjected to internal pressure of 160 and external pressure of 80 megapascal. All these are pascals, and says find the radial and hoop stresses at the inside, outside, and the mean diameters. Okay, it's fine. So take note there we have given this cylinder is subjected to two pressures. Take a note, internal and external. Be careful there. So actually let me collect data for you guys. These are two scenarios, but it's a one cylinder. But you must understand you have to break these to two parts. You must understand. I will draw like that. This part let me just remove that. This part will be dealing with an internal, we have internal pressure. This there, let me here write external pressure. So this is what we have. We have the cylinder, we have internal pressure subjected to internal pressure. Here's our cylinder. Also this, we have a cylinder, this side it's the same cylinder, it has same size, one cylinder. This subjected to internal pressure. I will show the area. This is an internal pressure subjected to internal. You guys can see that it's internal subjected. Then our radial, remember the radial will always act same direction as the internal pressure. Will act in the same direction as the internal pressure. These are radial stresses. Let me show those radial stresses with a different color, green. These are, or with that color, this will be radial stresses. Since it will act in the same direction as the internal pressure, radial stress will act in the same direction as the internal pressure. So okay, this is subjected to internal pressure. As you can see, this is it's our radial stress. You can just say there, radial. So here we are not subjected to nothing at the inside. Now this is subjected to external pressure, remember, but it still is the same. It's the same cylinder. It's not, doesn't necessarily mean these are two different cylinders. No, it's the same cylinder. It's like this. Actually, if I is something like that. It's subjected to internal and external both. But me, I decide to write it separately. But it's a one cylinder, guys. It's not the two cylinders. Just that simultaneously. So it's subjected to. This is the external pressure. Subjected to external pressure, right? So this is external. You can see those arrows represent external pressure. There, what I'm doing, subjected to a nice external there pressure. So the radial will act in the same direction with what as the will act in the same direction as the external pressure. Act in the same direction like pressure. We will act like that. Want you to note something. As you can see there. Let me use another color. That is a radial. I can indicate those to be radial. As you can check that. So these are radial stress. So we have two scenario here. So what I'm trying to say, we know when we are dealing with external pressure, we have its own distribution graph. When we are dealing with external pressure, we have its own distribution graph, like stress distribution graph. Let me try and construct stress distribution graph for internal pressure. You'll have something like this always. So you'll have 0. There is 0. From here we'll have something like this. When it reaches, you must know when you're dealing with internal pressure graph, internal pressure stress distribution, remember these lines, if you have watched my video, these vertical lines represent diameters, right? So this is a outside diameter which was given to be 145 meter. This is the internal diameter. I'll write it here. We've given the data. The external diameter, they say it is 450. I will divide by 1000 to pin meter. Then the internal is 150. I will divide by 1000. This will be simply 0.15 meter. So not forget, this is a internal pressure stress distribution graph. This one is for, we're focusing on what? On the internal. That is the graph. You must know this. Here we have a negative, and our hook stress is negative. This represent radial, or not hook stress. Radial stress is negative. Remember, the syllabus has changed. Then up here, then from here we'll have something like this, which is what we'll have our radial. We won't reach to 0. Radial hook stress cannot reach to 0. Sorry about this. That is the hook stress. This represent, we have hook stress, right, which is positive. Hook stress, it is positive, right? So yeah, then here we are given that it is subjected to internal pressure of 120 megapascal. Pressure is acting in the same direction as the radial. So when you are focusing on internal pressure is the same as radial stress. Make a note, internal pressure is the same as radial stress. So what I'm trying to say, that will be radial, but now radial is negative, will be negative 160, right? 160, but we know this is what it was megapascal at this point there. That is what will occur there at that point there. So at this point, that is where we'll have our radial stress to be negative. Remember, on the question is given as what? It is given as positive, but we know that internal pressure is the same as radial. Radial is negative, so we'll just say we'll change only we'll just put the negative 160 there. Then at this point, at that point is what is equal to 0. As you can see, 0 megapascal, right, at that point. So here we'll have, at this point, we'll have our hook stress. Here we'll have hook stress, but we'll have the minimum one, because this is at the external diameter, it's when we'll experience the minimum hook stress. Also at this point there, we'll have our hook stress, but that one will be maximum, like H like this will be maximum hook stress. So that is the stress distribution for internal pressure. Now let's check what about external pressure stress distribution. You will write the same thing, but the difference is that you must oppose everything. Let me show you. You'll have this. Must remember this line, vertical line, represent diameters. Those are diameters. The first one, always, you read it from the left. You'll go to this direction. We are moving to that direction from left to right. This will be internal. This will be external diameter. Those are diameters. Do not forget that, guys, please. So here I said this represent diameter. This is the internal diameter, will be the same as that. This is a 1. It is the 1 cylinder, 0.15 megameter. Then the outer diameter is 0.45 meter. So now it will change. You see, we started here and go here, and then we went upwards like that. But now we'll start from here, and then we go downwards. That is the difference now. There until we end it there. We oppose. You see there we started. Now we'll start upwards a little bit. So we'll start there at that point. Then it goes like that. But it won't reach to 0. As you can see, you just oppose. You just oppose these things there. Won't reach to 0. What we are doing, we are just opposing. So ladies and gents, here we have negative, we have positive. So this is simply indicating hook stress. Is for hook stress. This is for radial stress. Right. Then here we have 0. Remember, we have 0. That is 0. Now let us check our point. What do we have at external pressure? Continuing says in the internal diameter is that. And it is subjected, they say again, this cylinder is subjected. It is subjected to internal pressure of that. Okay, it's fine. And external pressure of 80 megapascal. External. I said external. When I'm talking external pressure will be acting in the same direction, guys. Does not change. Whether is a if internal diameter will be the same as radial stress, even though we are under, even if we are under external pressure, radial external pressure will be the same as radial stress, right? But the graph will only change the direction, will oppose that one. So what I'm trying to say, we have given the external pressure, which is 80 megapascal then. So we know that the hook stress is negative, then will be negative that point, negative 8 at that point, but we'll have that in megapascal. Do not forget we have this, but there it is 0. Obvious at this point it is 0. As you can see, it's at 0 megapascal. So here we don't know the hook stress here. Also there we don't know the hook stress. As you can see there, the hook stress there will be, you'll see it is higher than that, will be max. This one will be simply just mean. Yeah, we don't know the hook stress. So nevertheless, we are done with this graph. I'm just explaining. You see how slow I am. So you must understand, this is the stress distribution graph. We call these things, guys, this thing a stress distribution graph. Stress distribution graph, but is the internal stress distribution graph, external stress, external pressure, the stress distribution graph, internal pressure. This one is internal pressure, internal pressure, stress distribution graph, external pressure, like that. So yeah, nevertheless, let us attack the question I've just shown you. So we'll work hand in hand. We have this 1 and 2, this, but do not make a mistake. Does it mean we have the separate cylinders? No, it's the one and the same cylinder. It's the one and the same cylinder. Just that I'm making this simple so that we understand. So after all, I was just going to go to solution straightforward without explaining to you. For me, is to make sure that you understand, guys. That is the purpose why I'm creating this video. And nevertheless, click that notification button and subscribe if you have not subscribed to my YouTube channel. Right. So here they said we should find the radial and the hoop stresses at the inside and outside and the mean diameters. So it's fine. Inside, outside, and that. Want all of those diameters. So firstly, we can tell I will focus on this part. I will focus with internal pressure. You can start anywhere. Okay, I will start by this internal pressure. I'm focusing here. I'm working under internal pressure first. I'm working under internal pressure. I'm working under internal pressure. Internal pressure. I'll focus on the internal pressure first. So I'll work under internal pressure. What I can say, because we don't have A and B, let me just say solutions to make it easy. Solutions. You can say there, tell the examiner, I'm working under internal pressure, and then which diameter, because we have two diameters. We have this diameter and that diameter, internal and external. I can also make indication. I can say add internal diameter first. Right. So yeah, I'm indicating now. I'm focusing first at this diameter. So at that diameter, what is the radial stress at this diameter, internal diameter? Radial stress that the internal, remember internal diameter is this. This is 0.15. We said is negative 160 megapascal. There will be 160 megapascal. Simply add diameter. I'm just writing there at 0.15 meters. So yeah, I'm focusing there. We know we have given these. We don't know. And what about the hook stress? Remember, is this vertical? We don't know about the hook stress here at this internal diameter. So we'll just take what we know there. So nevertheless, we have this. Then, since we don't know the hook stress, let us move to internal now. What about let us move to external. What about the external diameter? At the external diameter, okay, we'll move. Okay, let's start by calculating a little bit first so that you're not confused. It's fine. We're still under. Let's first deal with this internal diameter. We know that the radial, it is given by A minus. Take note, there is negative. Do not use plus. Do not use plus here. It's negative. Syllabus has changed. There will be B over D squared. So it is the diameter. Use this formula as for what? Is the formula for calculating radial. But the formula to calculate hook stress, guys, it's A. You just here will have positive. B over this is one and the same thing. Do not confuse the sign. Remember, radial is negative. Okay, it's fine. What is radial there? we have negative 160. 160 watt megapascal times 10 to the power of 6 is equals to A, we don't know, B, we don't know the value of B, the diameter we know, working under internal, which is 0.15. You square this body, then you'll have 160 multiplied by 10 power of 6. We have A minus. So here is same as 1 there. You take that, like we punch it like that, 1 over 0.15, you square. Remember, but you multiply by the b, do not forget that b. So you punch this, we'll take it as a coefficient. So take that, punch that on your calculator, and say 1 0.1 over 0.15, square this guy, you'll get this to be 4,444. Then we have what? B. Do not forget the B. Then we'll have the B. You see what is going on there. So yeah. So yeah. Now it is maths. There's nothing we can do here. As you can see, we don't know the value. Okay, let's just call it equation 1. There's nothing we can do so far. We're done with diameter, internal diameter. There's nothing we can do. We have exhausted everything. So we come and say again, we're still under internal pressure, but now we look at external diameter. The external diameter. Whereby you can write it, whereby it's at D is equal to 0.45. That is, you can show it like that. That is our external diameter. What do we know? We are still under this graph here. Forget a bit about the external, we are still here. Remember this vertical line I said represent diameter. The first one is internal, the second one it is what? External. So what do we have there? The external. We have here, what do we have there? We have the radial, which is, we have given, is it is 0 megapascal, our radial there, that is what we know. Okay, then the radial there is equal to 0 megapascal. Obvious is at that diameter, it's equal to 0.45 is external, which is fine. That is what we know, but we don't know about the Hooke stress. You have not given. But however, we know that the equation to calculate radial, it's A minus B. It's A minus B over D. Okay, let me write D, big D, because it's external, D squared. So let's substitute what we know. We know this guy, there is 0. A we don't know, B we don't know, but the diameter we know, which is 0.45. We square that. So remember I said this will write as like that when you punch it on your calculator. So you do your thing there. If you punch that, you'll get this to be here we have 0 A minus 4,938 B. Do not forget that B, like that. So I can take this, because we have 0, I can take this to the other side. We'll have what? Positive. So I can say A, if I take that, B will be positive 4,938 B, just like this. So this is what we have now. We have that. So I can call this equation 2. So we have 2 equations now, can work hand in hand. I can say substitute equation 2 into equation 1. Remember simultaneous equations. So yeah, then I said substitute 2 into 1. Where is 1? Here it's our equation 1. There I can grab this. So here it's our equation 1. There. So let us substitute. What will be? A will simply, when we see A, will replace this A with that. It goes there. So you know substitution, right? We have minus 160 times 10 to the power of 6 is equal to 4,938b minus 444,444b. Right, so we have b's now. These are, can punch it on the calculator. These are those terms. Those, it's a one and the same thing. It's a matter of maths now. It's a matter of maths. You can simply say 4,938 minus 44,4444. It's a matter of maths now. Simply will get, this would be, you'll have negative 160 times 10 to the power of 6, then that side will have negative 39,506b. Therefore, still the maths. Okay, let me show you. Divide by that. We want to know, make b the subject, both sides. This and that will cancel. Negative and negative will cancel. If you punch that on a calculator, you b, supposed to get that b to be equal to 4,05 times 10 to the power of 6. It has no SI unit, it's just the value, that thing, right? Make no mistake about it. It's just a value. There's nothing more. Yeah, there's nothing more gorgeous and stuff then. It's just a value. You'll get this. We have our b. Since we have b, we can substitute this b to equation 2. This equation that we have there, you can find now the value of a. The value of a will simply equals to 4,938. Substitute that. Therefore, the value of a will simply equals to 20 times 10 to the power of 6. Right. So yeah, guys, so that is what we have there. Yeah. This is what we have so far. So yeah, it's a value of a, but now we are good. We're good to go. Now is nice. So we know that the radial, now we can substitute. We know that the radial, it's a minus b minus d. How nice is this squared? We have the value of a, which is nice. We have the value of that. Then we'll now we can find the radial in all the diameters. Okay, let's find the radial. Then now the value radial. Let me say add diameter. The first one, which was d is equal to 0,15 meter. Let me find the radial there. A minus b over d squared. Simply substitute there. What is a? we have A 20 times 10 to the power of 6 minus what is B? B is there 4,938 4,05 times 10 power of 6 B 4,05 times 10 power of 6. That is what we have. Then the diameter we know is that one 0,15. You square this guy there, then you simply project this to your calculator, punch that. Right, as you punch these values, you'll get your radial there to be what? What is that you got there? We are wanting, they said we should calculate what? Radial and hook stresses, right? Radial and hook stresses, which is no problem about that. So what did you find there? What did you find? It is funny that radial there, if you punch, we are given actually at that time it is fine is the one that I want to show you. It be 100 and negative 60 already we have given. Remember I said that the internal diameter we have said is equal to this, and we have set it the internal diameter, the what you call this guy. Actually, we have given, there's no need to calculate the radial. We can calculate the hook stresses. I just realized this will give me the same answer. Remember, we already have, you remember that the internal, the radial is that negative 60 at 0. So nevertheless we have them. So let us just calculate the, let's forget about this because we already have this from our question. Let us focus, let us, okay, let me not wrap there, we're still there, but let us check the hook stresses I've made here. What we don't know are who the values of hook stresses at this time. The value of hook stress, I can simply calculate the hook stress because that one we know it. Remember, the radial has been given to us at that diameter was simply equals to negative 160 megapascal. Remember, the internal diameter, the radial stress is equal to internal pressure. We've given this we've given even at the outer we've given to be 0, but let us focus in that diameter we've given, so we understand is no. Let us just focus just at this, in this diameter, it is internal diameter, but let us focus on calculating hook stress because we don't know hook stress. D is equal to 0,15. Let me find the hook stress like this. Hook stress is A plus B over D squared. Then the A, then you know it was 20 times 10 to the power of 6 plus B, which it was 4,05 times 10 to the power of 6. Here it is B. The value of B, divide this by the diameter, which is 0,15, then we square. We find the hook stress. This is the hook stress at the diameter, what? At this diameter. Let's find the hook stress. Some they like to write like this, then they write the diameter here like that. It's one and the same thing if you write it like this. If you punch, look at this, your Mr. Guy hook stress. would be 200 megapascal. It's positive, always obvious. That means this is a tensile. They won't ask you, but I'm just showing you this is tensile, guys. The radial, it is compressive, because there it is tensile. Because, sorry about that, because it was negative, the radial, it is compressive. The hook stress, it is a tensile. We got that. Fine. So let us check. We have the value of A and B, so there's no problem. Now let us find the, we have done with that internal. Let us find again at diameter, at the external diameter. Or just write it like this. If you don't mind, you can say also the hook stress at this diameter, 0.45 there. The hook stress at this diameter, you can say obvious, would be B over D squared. So A, it is 20 times 10 to the power of 6 plus B, which it was 0.05 times 10 power of 6, 4.05 times 10 power of 6. Then diameter is the one. You can write it like this if you want. 0.45, we square this, then the diameter there simply equals to the hook stress there at this diameter, simply equals to 40 megapascal. As you can see, we are getting positive values. If you get negative, you are wrong, because we have said hook stress is positive. So yeah, this is what you have. This is a new syllabus, guys, not old one. Yeah, we have found the tensile and the hook stress. We have radial, both we have radial, we have tensile and the radial. Yeah, you'll see. But what is left here? We're left with what now? Sorry about that. So we're done with the internal pressure part. Now it's fun. We have to go. This is a high order, is the one that is long. It's a high order question, little bit high, not that much high order, but you see, we are done now with this part. We have found everything, dealing, using, focusing on internal pressure. So we're supposed to go now to this guy now. Internal pressure, we're done there. We found everything under the external pressure. Now let me just do this to separate, to show that now we're focusing now on the external pressure. Now external pressure, stress distribution graph, external pressure. Now let us focus on external pressure. Okay, here is our graph for external. Now it's this one, this guy here. So yeah, we know what we do most. We can start by internal diameter. We have the given here -8, the radial there is -80 megapascal. Yeah, we know what to do. We can say, we can start at internal diameter. internal diameter there, 0.15 meter, so that examiner will know. We've given that the radial stress. If you like, you can write even the diameter here little smaller like this if you want. It's one and the same thing. If you want, you can use this method, but yeah, as long you've indicated, yeah, there's no problem. So we know that is negative 80 megapascal. We've given that, remember, external pressure is equal to the this guy, is equal to this guy. Yeah, it's equal to this guy. Oh, it's funny. Oh, what I've did here. No, it's fine. No. The radial. Oh, I forgot. I said you swipe the direction. I forgot to swipe it here. This graph. I said we swipe everything. No. Sorry. Everything must be swiped. What have I done here? No. Remember, I said to change the direction. It cannot be the same as like that. Sorry about that, guys. No. What I've did here. Simply. Sorry. It's not essential. It is not essential. Suppose they're supposed to exchange like this at this point. Don't know. They're supposed to remember, supposed to change the direction. So it is the opposite of that one. I don't know why I did. I've spoken by my mouth, but I forgot. Remember, this you just turn it around. This point you will take it to the other side. This one to the other side. Yeah, supposed to. This is how it looks like. You change. This point will be that one. This one will come this side. This one will go there. This one will go there. You will just swipe. So you just swipe the direction around. You see, you swipe it around. This is just external pressure. So cannot be at cannot be at. I cannot say at is that. Cannot say at this diameter. No, cannot be like that. This will be diameter of 0.45 meter. External pressure is equal to the radial at that external diameter, isn't it? So it cannot be this. Here it is 0, guys, as you have seen. Yeah, this is what you have given there. This is what you have given. So yeah, so we can solve, the radial, the formula. Add that. If you want to write it like this, it's up to you. It does diameter. We know the radial is negative b. Here's the formula. So which what? Negative 80 times 10 power of 6 equals to a minus b. The value of b we don't know yet. We don't know, but diameter is 0.45 u square. Now I'll try to be fancy. I can be fancy if I want, but let me not kill you guys with this math thing. Let me not kill you. with this math stuff here. If I like, I will leave it here and say equation 1, but let me continue it. Let me not kill you with the fancy maths, but I can, yeah, let me just be so average maths there, we know will be that isn't it? We have 4,938 b equation 1. Then we are done with that part. Remember, this was this diameter external. What about now at diameter? 0,15 at this diameter. It is the internal diameter, 0,15 meter. What about it now? So what about these guys? We know that we've given that the radial stress there is equal to 0 megapascal. Here it is, you can see. It's always, you see, when we see even here on our stress distribution curve, there is equal to 0, it at 0 megapascal. So yeah, now we can go about no radial simply equals to a minus b over d squared. Here this is 0, a we don't know, b we don't know, but this one would be b over 0,15. You square this, so have 0 a, then this will be minus know what to do. I've been showing you there. Be 15 square that. This is 4,444b. Then I take this to the other side. Simply have a to be equal to 4 positive b. Call this equation 2. Then I use substitute. I can say substitute equation 2 into equation 1. Where is equation 1? Here it's our equation 1. So a 44,44 b. Remember, here it's our a. You take this a, substitute so yeah, b minus also this minus again 4,938 b. So 44,444 minus 4,938. Okay. 39,506 B. Therefore, the value of B will simply be negative this time. The value of B will be negative 2,025 times 10 to the power of 6. Then what about A? Here it's A, but we know that A we have said is this guy. This will be 4,4,4,4,4,4,1,2. Remember, this thing, they have no SI units. We are done with value of A and B. So yeah, we know what to do. We can find our radial. I can say, okay, radial we've been given. There's no need, which is, we know the radial at internal. When you're dealing with external pressure, it was 0 at external. It was it was 80. So there's no need. It was -8. So let us find the Hooke stresses. Hooke stress at 0.15 diameter. No, this is A minus B over D squared. 8 minus 90 times 10 power of 6 minus B. This is minus 2,25 times 10 power. Then B. Hooke stress, ne? This is wrong. Okay, it's positive. Hooke stress. Do not make that mistake. It is positive. Remember, it must be plus. The formula of it must be plus the 1. Let me check to the other one I've made correct. Okay, let me check the other Hooke stresses in our previous that I did not make any mistake when I was calculating. Okay, positive, which is fine, no problem. Our formulas, I was just double checking, were correct. So yeah, positive, negative 2,025 times 10 power 6, that is B. The diameter, which is 0,15 squared, as you can see there, punch this. Hooke stress must be positive. I don't know if you get negative, then something else. Depend. It depend on, we're dealing under what compression, right? That means will change, will be compressive, but yeah, it's what it is. That means the Hooke stress would be compressive. We have negative 100 megapascal. So this is simply that is compressive this time. Remember, this is a external pressure. So yeah, will be compressive, no problem. But if you are dealing with internal pressure distribution, if you find it negative, it will be wrong. If it become that's negative, if you are dealing with you check the diameter 0,5, it will be A plus B d over d squared. Value of a is 90 times 10 to the power of 6 plus 1 is b is negative 2,025 times 10 to the power of 6 all over 0,15, not 0,15 this diameter again, 0,45 squared. So yeah, what would be that the value there, the hook stress then simply equals minus 80 megapascal. Simply shows this is compressive. So we have this, we understand, right? We have, so let's say for argument's sake you are needed to calculate the resultant stress. How can you calculate the resultant stresses? Let's say I want to calculate, let me add my own resultant stresses. How can you calculate resultant stresses? To calculate this guy, we have to formulate some nice table there. You can formulate some nice table there. Okay, just to formulate some table there. We have the first table. The first one will be for, we'll write diameter. So diameters. Then we'll have the following table. You can write it internal pressure. Then you can have another table there. You can have, okay, is external. You can have this. You can make it smaller because this will be for values. Simply just for the values. Right. Then after that you write, you sketch another. This is for external pressure. Right, so sketching our table there, formulating this table. It's for resultant, it's how we'll get our resultant stuff here. So you can say the resultant so yeah, we have this table there. We have two diameters. Remember, we have given what is the diameter that we had. We had 150 diameter. and we had 450 diameter. Remember what that was, millimeter, right? Millimeter. We had these diameters, so it's fine. This side will obviously, we're dealing will have hook radial stress, also have hook stress, radial stress. You have hook stress, radial stress, then we'll have some hook stress like this. So this is what we have. So what was the okay, we have diameter 150 diameter. What was the internal, what was the radial? We make the correspondings there. What was the radial there? You'll find out that the radial, it was we had minus 160 at this diameter. Remember, with 160. Remember here we had what, 0. We're taking from here, from what we have before. You remember, this is what we had at this diameter. We had this to be negative, that negative 160. There we had it to be what, 0. So yeah, substitute what we know. What about the hook stress? Is the one that we have calculated under 150 diameter. Like you go like that. You see, this column is for 150. This is for 140, going down like that. Then this is for, what was the hook stress there? We found it to be positive 200, isn't it? Then what there it was, what was the 150, what was plus, we got it to be what, 40. The hook stress there, it was 40 at the initial stage. We got that to be what, 40. Here, if you remember it, here we got this to be what, 40 megapascal. Put our thing. Then we focus on external pressure. On external pressure, our radial was equal to the external pressure, which is why we're given, which is, it was which is we're given at this diameter 150, it was 0. Remember, there we've given at the external diameter of 150, it is external, it was negative 80. You remember it. Then the hook stress we just calculated. Remember, here we found at the internal to be 180. There we got to be negative 100. Here 180. Then there we got it to be 100. Where is our 100? Here 100 at diameter 0.15. No, diameter 1.5 it was, yes. Then at this diameter it was 100. That is what we got. So what about now? Now we'll focus on the resultant. If you want the resultant, you simply now you add the stresses. The radial, remember, is for radial. As you can check, you add the radial. This column you add like that. Just add 0 plus -8. You start where is starting from here. Start from here, pay at the top, -180 plus 0 will still be negative what? -160. There's nothing that will change there. As you can see, with did here we'll have -160. If we add, remember focusing resultant at this diameter. Now we come, you go to external pressure. We have added this one. You come again, you add this 0 plus -180, which simply equals to -8. You add just like that. You come to the hook stresses, you add the 200 plus 40 will be you have added this one, right? Then you come to the hook stresses. You have 2 hook stresses. How did I've added wrong? I'm tired, guys. Sorry about this. We are not adding like that. Let me do like this. How do we add this? You cannot add this diameter. They are not the same. Sorry, forget about that. We are adding what is in the column. Remember, this column like this column going downwards. This column going downwards like this is for what? Is for 1/5. You add going down, you add via the diameter. That column is for, you cannot add the diameter. They are not the same. We focus on this diameter. This column going downwards is for 1/5. You come, you add the radial, -160 plus, still under this column of 1/5 plus 0, the radial. This is radial, this is radial. Will be what? Negative. You get the resultant to be -160. 60 plus 0 is that. You come again, we're still focusing on radial. Now we are done with this diameter for radials. Here we are done. I've just taken, we are done with the radial. I'll make the ticks like that. You can highlight the ticks that we are done. Now you come to external diameter. You add 0. You add with -80. Simply equals to what? -8. We are done. Now we're left with hook stresses. That 200 plus 180. 200 plus 180 same as 200 minus 180. So we are done with those. The one that we have circled, we'll have what there? +20. Simple. Just have 20. Remember. So what we left with, we are done with these parts. We are done with this. Now let me check. We are left with these two. 1, 2. What we are left with this. Others, we come to the hook stresses. We have 40 there plus the hook stress here, which is negative. I want to cancel there because you come with those hook stress. Okay, this empty the radial we did not focus on. We come again to this diameter now. Remember, we're focusing on these coulombs. I don't know what I've did, but let me do like this, guys. Seems like I'm doing some mistakes. Okay, focusing on this coulomb, guys. 150, you add to negative 160. You come, you add it also with 0. Oh my god, not allowed. Would be, we'll have this, right? Then we come to hook stresses. 200, you add with negative 180, you'll get positive 20. Come now to external diameter. 0 of the radial, you add with other radial, which is radial is 80. 0 plus minus 80, this will be negative 80. Then we come to hook stresses. There we have positive 40 plus negative 100, simply give me negative 60. So this is what it is. Your resultants are these ones. It's how you get, this is how you'll find your resultant. This coulomb, you see how you find your resultant, this one. Then we're done with this resultant. That's how you find it, guys. So thank you for watching. Please do not forget to subscribe to my YouTube channel and click that notification button so that you'll be notified whenever I post a new video. Stay blessed. Share this to your fellow classmates. Feel free to comment and like. All the best.